there any questions from the previous class? I mean, either everything is completely clear or everything is completely unclear. Okay, so what we were trying to do is basically trying to compute correlation functions in the Ising model with using mean field theory. And we said that basically it's good to start with putting a magnetic field at each side and then just look at the kind of a response function. So if we put, then the Hamiltonian becomes like minus and then put a field at and then we said that the correlation function is basically given by let's say C of this depends on this difference. Okay, and so this is defined as sigma x bar m square. So this is 0 above TC and finite below TC, and we are basically looking at the correlations in the fluctuations, right? And so I mean you can just set 1 to 0, and then this is equal to, okay, so finally we are interested in the correlation function for 0 field, but we put on a field and then look at the response. So we said that C x bar is equal to del x bar and then 1 by beta. So this is of course completely exact, right? This is a completely exact equation where mx is the expected magnetization at site x, and this is the change in the applied field at some site x prime. So basically this is the response function, this is a correlation function, and they are related by this simple relation. Okay, so then we want to compute this using mean field theory. And so for that we basically wrote the free sort of the variational free energy. So we said that the variational H naught is now minus and so the variational free energy is just minus half So okay, there's one more term, right? Okay, so this comes from so this is H average 0, this is H0 average, and then there's the free energy, which is let's say and so what is M? M is again just the magnetization at each site. Again, we used calculated using the variational thing. So that is just equal to tan x bar. Right. Okay, so and then if you do this, basically take this del phi by del So this and this basically you have if you put so finally we want this equal to 0 gives you a set of equations from which you can completely determine the this h of x bar, right? And once you determine this, you also determine the magnetization profile. So that's the idea. So you have a set of n equations and n unknowns, and so these are the equations. And when you if you plug this in and take the derivative, which is not very easy, not very difficult, then basically what you get is minus half. I mean, so the final answer is very simple to remember. It's basically that the variational field Hx bar m is just sum of all the effective field coming from all the other spins plus the external field. Right. So the final answer is easy to remember. Like when you solve this equation, finally you get this set of equations. So now, of course, you have to solve this and this, and you can completely determine this unknown quantities, which are these mx's and the hx's. Right. Okay, so so obviously it's a difficult set of equations. For if I arbitrarily give some hx's, then it's difficult to solve, right? So, but what we are interested in is kind of this object del mx by del hx prime, which will be simpler to handle. Right. So, what we'll do to solve this equation? So, we have these two set of equations. Is to say that, let's say these applied fields are very small. Okay, so if the applied field is very small, then we can basically kind of expand this. Okay, so first of all, let's write this as let's invert this equation. So we get hx bar equal to and this is equal to there was another form for this, right? This is correct, right? Okay, so if we can write it like this, and now we want to let's say these fields are small, so actually it doesn't matter, let's use this only. So 1 by beta which one? This one? Hx. Okay, so let's write this as m plus okay, so what we are saying is, if we supposing initially h is 0, so then you have some magnetization which we already know, right? So we know that that is given by what? If h is 0, then how do you find the magnetization at any given temperature? Yes. Yeah, so that is the solution of this equation, right? Sin hyperbolic of beta j tilde m. So if h is 0, that's the solution. Okay, now we apply a very small field everywhere. Right? Then we expect that it should change by some small amount. Right? Yeah. So if it changes by small amount, then we can do Taylor expansion, right? So if we do Taylor expansion, we get 1 by beta. First term is of course tan hyperbolic inverse m. Right? And then the next term is what? Okay, so you have to do derivative of tan hyperbolic inverse and so on. But the final answer is, so I'll just write, it's 1 by beta So you're doing an expansion around this equal to 0. So first term is this, then you take derivative and put, and you get a coefficient delta mx and then delta mx square and so on. So we just keep till delta mx. Okay, so if you do this, then now you just put this back into this equation. Okay, so then we can get everything on the left hand side in terms of m. Right, so it will be an equation of involving delta mx. Okay. So delta mx are the unknowns now. Okay, so use this into this equation. So then we get basically is equal to sum over here also you do the same. So n plus delta mx prime bar and then plus hx bar. This line or this line? Here. No, this, you're saying this one. No, so initially field is 0 everywhere. Okay, so then of course the magnetization is the same. So I'm expanding around that state. So then of course it's independent of x. When h is 0, all the hx's are 0, right? Then of course you expect uniform magnetization everywhere. And then I put a small field which can be different at different places, right? Then of course it will change everywhere. It will depend, the change will depend on x because I will put a different field at different sites. But the this thing is the same, right? So constant thing plus a different thing everywhere. Okay, so now I have this equation. This is fine, everyone. Okay, and now I see that this object is what I called what? What is this object? J tilde, right? Okay, I mean, other people other than he also should answer because otherwise, I mean, he's answering everything. Okay, so this is J tilde, and then what happens is J tilde times this thing, and this thing cancels because that's the equation satisfied by the constant field. So these two terms cancel. Okay, and then you have a nice equation which is basically okay, and this one is also a small field. Okay, so because we said that we started with 0 field and then applied a small field. Okay, so let's just call it delta hx bar. Okay, so now we are almost done. So what we can do is basically get an equation for the correlation function from this. Okay, because the correlation function is basically del M x prime okay, apart from okay, so that's how we define the collision function. So if we divide everywhere by kind of delta H, then what we get is basically equation for the collision function. So minus uh, okay, so I'm taking derivative of this equation with respect to delta H at x equal to 0, okay, because, and using the fact that everything is translationally invariant. Okay, is this clear? And I got this KBT because there was a 1 by beta here. Okay, so if I divide by beta and beta, okay, so now this is I mean, the good thing is this is a linear equation, right? And we know how to solve linear equations when there is translational invariance. So how do you solve this equation? Fourier transform, right? Yeah. So so then we just basically multiply this by e to the power iqx, right, and sum over all x. Okay, so if we do that, so multiply by e to the power I. So let's say assume we are on a periodic lattice. So q bar takes so q, if we are on a periodic d-dimensional lattice, then q bar is some 2 pi. So let's say this lattice is like linear dimensions are L, so and this L goes from 1 to N, or minus N L by 2. Okay, so if we multiply this equation everywhere by e to the power I, and then take a summation over x, then what we get is, so here you have sum over x and x prime. Okay, so where this object is basically okay, so now this we just call it J tilde Q, and this is C tilde Q. Okay, there was a minus, I think. Okay, so now we have C tilde and we can get Cx by just inverting this. Right, so C, is this visible or no? Yeah? It's okay, no? Okay, so C of x bar is therefore equal to, okay, so this L is basically in each direction it is L. Right, so the total number of points is L to the power D, and then we have sum over. And then if you assume that this L is large and so on, then you can always convert this summation into integrals, right? So if you do that, basically what you get is okay, and this integral probably also again you have done in yesterday's class, I guess, in Sanjib's class, when you calculated first return passage. I mean, I think it's more or less exactly the same integral. Right, and so how, I mean, okay, so when you see this kind of integral, and what you're interested mostly is in large distances, okay. So what we'll do is that if x is large, then this kind of integrals are usually dominated by small q, okay. So then we want to look at this function at small q, which means expanding this around q equal to 0. Okay, so if you expand this function around q equal to 0, what we'll get is j tilde q bar is equal to when q equal to 0, what you get is actually exactly that j tilde, right? Because it's a sum over all x. So that is just j tilde. This is our old j tilde, and then the next term will just be q square. So, so you'll get something. Let's say, let's just put it as 1 plus alpha q square. So let's assume that this has this form. So if you, for example, if your jij's are such that only these things are non-zero, nearest neighbor sides, then what is this function j of q? Cos k, right? Yeah. So in 1D, I mean, so it's basically like let's say j is so the definition is j 0 I e to the power I q I. Let's say in 1D, right? This is the definition of j tilde. So if the definition is that only for x equal to 1 and minus 1 is non-zero, then this will just give 2 cos q, right? And then if you expand this, of course, you get 1 minus q square, right? So if you have more nearest neighbor interactions also, if you expand, finally you will get q square. I mean, that is general. I mean, given that this doesn't have some asymmetry, in which case you would get q q. Okay, so so in general we'll get something like this, and then we just plug it in here, and so I won't write the, so after some simplification, what you get is, let's say out here you get, and in the denominator you get q square. Right, so basically you have a q square here, and you take all the constants together and do some simplification, and basically you'll get something like this, where k is some constant given by okay, and now this integral you can simplify a little bit by, because this is like it looks the same in every direction. So instead of dt q bar, you can do all the integrals and just reduce it to a single integral, right? Okay, so so if you are looking, if you are fixing x in some direction and calling the distance r, then in that direction c of r would be 2 pi d. So okay, there is some constant here which I am forgetting, and then basically to the power minus dqr. Okay, so okay, so this thing I won't do the integral. So this you can basically, for large r, you can kind of there's some way to see how it looks like, and final answer is like it looks like this. I mean, e to the power. Okay, so this integral, I mean, you can look up in some standard book. There's some tricks to do this, and you can easily get this. Okay, so now we have got two things. One is like we see that, okay, so there's this correlation functions, correlation length, right? So it looks like, I mean, okay, so this, if you look at correlations, they decay exponentially, and this is the length scale over which it decays. I mean, this is much stronger than this. So if this is there, then you can forget this, and you get a length scale over which correlations decay. Right? So this is zeta is called the correlation length. Okay, so I mean this calculation is is done with zero magnetic field, and if you are above TC, then of course m is 0, right? So if m is 0, this looks like what? So xi, if above TC, t greater than TC, m equal to 0. So this should be clear, right? Now there's no magnetic field. I mean, I had switched on those magnetic field to do the calculation, but now because I expanded in linear order, and then everything I got is by taking derivatives. Now, I mean, I can imagine that there's no magnetic field. So these answers are now for zero magnetic field. I mean, so I am just evaluating correlations for zero magnetic field. So for t greater than Tc, m is 0. So xi, this, what is this, xi or zeta? What is, xi. Okay, Okay, so xi is basically some constant, but the main point is this is like so m is 0, so you just get beta j tilde. So beta has 1 by t, and this is tc. J tilde is just tc, right? So t minus tc. So it's t minus tc, and then there's a to the power half. Okay, so it's clear that from above tc, as you approach tc, this correlation length diverges, and at tc, so this is infinite. So at tc, I mean the correlation is just given by a pure power law correlation. Sorry? So that's the general form. So in this mean field calculation, eta is 0. So I mean, yeah. So in general, you expect right. Yeah. So okay. So at so this is the mean field result, right? So I shouldn't put equal to when I write things like that. I should just put something like this. So this is mean field, and if you do, I mean. So mean field theory basically eta is 0. So this may not be the correct answer. I mean, this is what mean field theory gives. Okay, so here again you can do the other thing, like you can approach either above TC or below TC, from below TC, and in both cases you'll find that you get a different, so for if you are TC less than TC, you'll find that psi is this goes as okay, yeah. I think it's a small value. I don't remember actually. Does anyone know? It's small actually. It's small, but maybe it's like 0.2 or something. I don't remember the. Of course, it also, I guess. Okay, so the other thing I just wanted to say is that below TC, if you do the calculation, you can't put m equal to 0. You have to write the correct expansion. And then what you'll find is that it also looks like this. So it is TC minus T instead of T minus TC, and there's the prefactor is slightly different. So I won't go through that. Okay, so I mean this basically means so whenever you have so at critical point you have basically power law correlation. And I mean the sort of important point is that there is no length scale. So power laws, whenever you see power law, means there is no length scale in the system. Which one? This one? Yeah, yeah, yeah. So that's what I said, that for t greater than tc, I just, this is a general expression, both t less than t and t greater than tc. And then what I do is, if t is greater than tc, I can just put m equal to 0 and I get something. If t is less than tc, I have to be careful, okay, because even though m is very small, I mean it's order of 1 minus beta j, right? So I have to keep that term also and then simplify and see what I get. And if I, exponent is the same, right? Only the prefactor will be different. I think if you look at susceptibility, usually they are different on the two sides. Yeah, I think, yeah, they're in general different. Okay, so, no, so usually if length scale means, like, if you have, see, if you have an exponential thing, this is the length scale, right? But here, if you kind of, how do I say, I mean, see here, if you go beyond a certain length, I mean, it's basically uncorrelated. Okay, here also, of course, if you go fast, it goes to zeros, it becomes small. But the point is that if you, I mean, like any quantity you take, if you divide by some length scale, it's, okay, I mean, in some sense, it just, okay, so how do you get a length scale from this? If you had some power law, see, there's nothing to get, like if you have a Gaussian, you say that this is the length scale, right? Because after this distance, it becomes, I mean, like really small. But here there's no, I mean, this, when you write a power law, there's no length scale, right? So there's nothing to compare with. Okay, that's one way of looking. I mean, yeah, that's what I can think of right now. Sorry? It's of course much slower. Power laws are much slower than exponential Gaussian or anything. Huh? Yeah, I mean, of course, if it's a big power, you might think it's decay sufficiently large, right? But in 3D, you can say it's quite small. Okay, so 3D is, actually in 1D, it's kind of strange. If you put d equal to 1, you get nonsense, right? But in 1D, actually, this whole thing is kind of meaningless, because why? Huh? Very less neighbors. Anyone else want? He says there's no phase transition. Yeah, there's no phase transition. Yeah. So here, everything here, we are assuming that there's a phase transition. So mean field theory is bad in the sense that it tells you, it doesn't tell you which dimension it will work in, right? I didn't put in dimensions anywhere. When I did the calculation, it was in any dimensions. And I get a phase transition, but obviously it doesn't work in one dimensions. Okay. Okay, so let's just summarize what we have got at the end of the day. So, I mean, so we saw that, I mean, mean field theory basically does predict a second order transition. Right, so it does give us a, like, magnetization as a function of temperature nicely goes to 0, right? At least that we get thing, but it may not, of course, be right, and it gives us a value for the temperature, which is a simple formula. Okay, so I think if you do Ising model, this might be maybe 2 times this. Okay, so or 0.5 times this. So it's very close to what you do in, like if you do actual calculation. And as you go to higher dimensions, it's better and better. Okay, so the predictions of mean field theory are good in higher dimensions. Then it gives us values for critical exponents. So I should say actually you can also, using mean field theory, you can also study first order transitions. Like, so in our model, I mean, if you are below TC and you change H, you will go from some plus M to minus M, which is a first order transition, right? So you can also study first order transitions with whatever equations we had. I mean. And here we got like M goes as let's say t to the power beta equals to this specific hit, and susceptibility is goes as to the power minus. Okay, so what else is there? Okay, so we did in mean field theory in a certain way. Now I just want to briefly tell you about like how to relate this to the usual sort of lambda mean field theory. Usually what it does is it starts with a sort of phenomenological free energy, which you write in terms of the order parameter. Okay, so here you just start with, let's say, phi lambda is equal to, like, you assume that whatever free energy you write, it should have the symmetry of the original system. Okay. So here we have magnetization, and we know it has this rotational symmetry. So basically you write all terms which satisfy this symmetry. So that way, if you write, what you write is something like, and you write something like half. Okay, so I mean, usually when Landau does it, he does it in kind of continuous thing. So instead of sum over all sides, he does it, imagines it's a field thing. So you just do it in. So imagine you have a field which is a function of x. M is a magnetic field which is a function of like is the magnetize the order parameter, which is a function of the space. And then you have these terms, and finally you have a term which looks like grad m square. Okay, so this Hamiltonian obviously has the symmetry m2 minus m, and this is the simplest thing you can write. Okay, so I mean, you just do a Taylor expansion. You don't have odd terms, and if you put a magnetic field, then you include that. So then you put minus h. Okay, so now, so we can kind of get this from the Hamiltonian that we wrote. Okay, so I just want to point that out. And in this Landau theory, what you also put in by hand is that these are functions, given functions of temperature and whatever parameter you have. So, I mean, simplest thing is you can just assume they are function of temperature. Right. And I mean, one thing can also put in is that this changes sign at a particular temperature. So, and so that's the transition temperature, and then you are interested in things around that point. Okay, so it's a phenomenological approach, and let's just quickly see how this connects to this mean field that I described. Okay, so basically what we did is we wrote a variational free energy. So here also if you minimize, if you ask what is the minimum free energy configuration, then it's clear that if you don't have a field, then you should put constant m everywhere, right? I mean, it should just be independent of position. So this goes to 0. And then you can just minimize this object, m square plus m4 plus m6. And then the idea is that you have this kind of profiles. I mean, depending on the sign of P, I mean, you will either get a single minima or a double minima and so on. And then you can understand what happens at different temperatures. Okay, so that's the, yeah. So now we also had a variational free energy, which we wrote as okay, now I'm saying this and this are kind of the same object. Okay, so is that obvious? So how can I show that these are the same? Huh? Small m. Okay, so one is that I should look at small m. Okay, so this, huh? What? Yeah, I can expand around m. So then, of course, I'll get these terms. I mean, m square, m4, because these are local terms, right? So this will give me m square. All this m to the power m's. And then I need this object. This should go to this. Right? That is also kind of clear, I guess. Okay, so to show that, I mean, basically what you can do is that, okay, so supposing you just have, okay, so first of all, you can write this as equivalently as 1/4. Okay, so this, I mean, it's easy to see because if you square this, you get a mi square and mj square, and if you sum over this the other index, you'll get j tilde, right? So the square terms will basically cancel with this, and the other mi times mj, the product terms will basically give you this object. So this and this are the same, and then of course, so this is the local term, which will add to basically this part, right? So this will add to this part. So from here you will get m square. When you expand this, you will get a mi square, and from here you get a j tilde. So those two will combine to give you this b of t. Okay, and the good thing is that this already has a temperature, and this has j tilde. So you see that, okay, so when you expand this, what you will get is, I mean, you'll get something like kBT times m square. Right, the first term will be m square. Now from here you have something which is minus j tilde times m square. Okay, so you already get something automatically which does change sign across at the transition temperature, which is, of course, you know it has to be like that. So, but it's good to see that you get this you automatically get. Okay, you don't have to put it by hand. And then this term is like if you have, for example, nearest neighbor interactions, then this is basically gradient of m square. So this is just the discrete version. If you go to the continuum limit, this becomes gradient. So that's basically this term gradient of m square. So this thing is basically the equivalent to the yeah. But so this okay. So I won't go through the details again. I think what you can do is in the tutorial basically. So I won't be there. But I would, I think you should just sit and just work through this. Okay, so show that if you expand this, you get this, and with the all these terms, pt, ct, dt will be something. So I'll write the form of this. What you get if you just so do the steps. Okay, so C and D don't change sign, but B changes sign across the transition. Okay. Okay, so this phi of L that I wrote, so this is also called the and so in general, I mean, of course, most often you don't do a microscopic derivation. What you do is, I mean, so this is okay. So basically, you assume that like whatever energy the thing you are going to write, it should be like a small Taylor expansion, okay, around 0. And then it should have some like terms which are gradients, and it should have the same symmetry as the original Hamiltonian. Okay, so okay, so the last thing I want to do is this. So there's this Ginsburg criteria. Okay, so one other way to look at mean field theory is to see, like in our, we had this spin term in the Hamiltonian, and we basically kind of wrote it as, let's say, sigma I. Okay, so this is like delta sigma I. then we got terms like mi, mj, and then there were terms like mi. Okay, and in some sense, what we are doing is kind of looking, neglecting this correlations in some sense. Okay, so we are effectively looking at these terms and dropping second order terms because we kind of looked only like linear fields. So it's like dropping this term. So in some sense, we are neglecting correlations, and so if correlations are not that strong, then we might expect that maybe it works well, which is true in higher dimensions. So one way to check like if correlations are small is because we have calculated the correlation length, right? So what we can do is use that calculation to check, kind of see how large are these correlations, okay? And especially at given temperature, how large are these correlations, and then it gives us a kind of self-consistent criteria as when it is expected to work well. So if we do that, so we should basically compare, let's say, I mean, things are correlated up to the correlation length, right? Z. And so we can look at what is the average correlation in this volume. So that is given by DDR, C of R, let's say 0 to Z. Okay, so this is the kind of total correlation in a given volume. As a kind of average correlation, right? And then we have to kind of compare it with something, and we could compare it with, let's say, the, I mean, just dimensionally, we might compare it with the average magnetization square, right? Because these have the same dimensions, like both are sigma sigma. So this is a good thing to compare. So if you do this, so now we, like at least if you're close to TC, we know what this looks like and what this looks like. So, so what we know is that this this object should be roughly, I mean, this goes as 1 by r to the power d minus 2. So this should be basically what? I mean, so if CR goes as 1 by r to the power d minus 2, so what will this integral be? D minus? 1 d. I hope it's not log because that's. Okay, someone say log. Okay, log is not good because it will make life really complicated. I mean, I hope there's a better answer. Okay, at least someone make a guess. I mean, why is it just only he is making the guesses? And say something at least, right? I mean, how do I know that you are r square? So okay, so what did you do? R to the power d minus 1 by r to the power d minus 2. So that's r. So it looks like r square zeta square. And this one, I mean, what can we say about this? Okay, so what we know is that this is independent of R, right? It's a constant, but it depends on temperature. And how does it depend on temperature? Huh? T to the power beta, right? So what should I put here? T to the power 2 beta, anything else? Zeta, not zeta, but zeta to the power d, right? Okay, so I hope it's correct. I'm not sure now. Okay, so now this, and zeta is what? Zeta is also related to t, right? So zeta is t to the power minus 2 nu. So that's t to the power. Okay, so let's forget this, assume it's positive. 2 beta, and then this is t to the power d nu. Okay, so finally the whole thing is Okay, so then if t is small, then if this object, what is necessary for this to become small at near the critical point? This should be greater than 0, right? If it is less than 0, then this thing will become really large. So what we need is d minus 2 mu minus 2 beta should be greater than 0. Okay, let's see if this is correct. This is the correct. So this is the Ginsburg criteria. Okay, so if this is greater than 0, if it is less than 0, it is 1 by t, right? So then t small means it becomes very large. As you go towards the critical point, it becomes really large. So correlations are really important, right? And if it is greater than 0, then of course t to the power some big power means it becomes really small as you go towards. Okay, so in our also, I mean, if you from mean field theory, if you use beta and nu, those are both what half, right? Mean field calculation, both are half, right? It's gone here, right? Beta and nu both are half, so then you get d greater than 4. So for Ising model, d greater than, so d equal to 4 is the critical dimension. Above 4, you expect mean field theory to be exact. Okay, so that's okay. So basically, I want to look at in a, I mean, like roughly what is the average correlation in a given volume? Okay, so correlations, of course, die beyond the correlation length, right? So in a given volume, I'm just calculating the average correlation. Okay, so this is the and then I'm comparing it to the, let's say, the average magnetization, because they have then both are like same dimensions. And so this one, this is clear, is it? This square, and this one, this is clear. Okay, so then I put z equal to t to the power minus nu. So then I do something and I get this. And then I say that if I have some t to the power a, if a is positive, then of course this becomes small, right? When t is close to 0. If t is negative, then it's 1 by t to the power a, and that becomes large, right? When a is a. Huh? If a is less than 0, then it becomes like 1 by t mod a. So if t is small, it becomes blows up, right? So then correlations are, become very large. So then we know mean field theory won't work. So that's why this greater than or less than 0 decides whether mean field theory is good or not. Okay, so okay, so now the other thing that I'll briefly talk about is like, okay, so we talked about that. This gives the upper critical dimension, right? So you can do this for any model, like any of the spin models that I discussed. I mean, the calculation will of course be different. You have to do slightly different things, but it's not very different, and it's not more difficult than what we are doing here. One good place actually reference is this book by Carter. And he also has a lot of lecture notes on this MIT page. So I think either the second volume or the book. So sorry, second volume or internet. I mean, so on his MIT website, there are notes on this mean field theory, which you can, which is for general spin models and so on. Okay, so. Okay, so the other thing I want to do is basically, can we say something about the lower critical dimension? Okay, so how, so I said lower critical dimension is the dimension below which you can't get a phase transition, right? So does anyone have an idea how you would go about this? Someone say something. I mean, make a guess. I mean, what would happen? I mean, Ising model, like, can one prove that? How do you prove? I mean, is there a simple way to show that there is no transition in 1D? Domain. Who said that? Good. Okay. So what do we do? Okay. So Ising. So I mean. Okay. So let's say. Okay. So this is called the Landau. Okay, so what you say is that, let's say at t equal to 0, if you look at an Ising model in one dimension, then of course what will the state be? It will go to a all ordered, so this ferromagnetic Ising model, so obviously it will go to a state which has all spins up. Now let's imagine, so this is at t equal to 0, we know that it will certainly be either in this or all down, okay, but let's put the system in this state, and then let's put a small temperature, okay, so let's put a small t, okay. Now what we want to prove is that as soon as you put any temperature, this thing will just go to zero magnetization, okay? Which means that, there are configurations which cost very little energy, but are sort of very important because there are a large number of them, okay. So that's the basic argument, okay. So the idea is that when you write the free energy of a system, so it has an energy and also an entropy, right? Okay, so at 0 temperature, of course, there's no entropy. It's just, let's say, in the ground state and it starts here. Then if you increase the temperature a bit, so there's some energy cost. So if you look at slightly excited configurations, they have some higher energy, right? So energy increases. But they might be good if there are a large number of configurations like that. Okay, so the entropy of that kind of excitations is large. Then you know that the overall free energy can go down, okay. So in that case, that kind of excitations can be easily produced, okay. So basically in Ising model, what you can easily see is that, okay, so here what you can do is you can easily, so what is called like a domain wall excitation, which basically is a configuration like this. Up, down. Okay, so how much energy does this configuration cost? So my Hamiltonian is this. Okay, so H. Right, okay, so how much does this cost? So obviously the energy increases, right? So it must be 2J. It says 2J, I guess. And what is the entropy of this configuration? Log n, okay, because I can, this position of the domain wall, so this is called a domain wall because it separates up spins from down spins. So this can be anywhere along this chain, okay. So roughly there are L such configurations. So this delta S, the gain in entropy is kind of, so therefore change in free energy is equal to 2J minus KB log L, right? So if L is large, I mean we are always interested in large L, the free energy always goes down, right? Huh? So irrespective of temperature, if L is large, then the free energy will always go down. So this kind of excitations will easily occur and destroy the order in the system. Because this has zero order, right? I mean typical domain wall configurations, they just destroy the main. Okay, so this is the argument why, I mean, and it's actually, it can be made complete, I mean, right now it doesn't look completely rigorous, but it can be made completely rigorous. That's what Payal did. Okay, now this is in 1D, and in 2D you can try to do a similar thing. Let's see what happens if you do a similar thing in 2D. So, okay, so 2D, I mean, ordered configuration would be like this. So again we start with t equal to 0, right? Then of course it will go into this kind of a state. And now we increase the temperature a bit. Okay, so now so what kind of excitation should we look at? I mean, can we do the same kind of thing? I mean, like if we, yeah, so can you think of an excitation which will also again destroy this order? So it has to be excitation where you get zero magnetization, right? If you have to destroy so you can't just flip one spin. So what kind of an excitation would you look at? Okay, so what basically, yeah, I can basically take I can look at a configuration which is like, let's say I have to flip a large number of spins, right? So the simplest thing I could do is like flip, I mean all spins like this. Okay, so again I create a domain wall. Okay, and these are all up spins, all down spins. Okay, so this is a domain wall of some length. Let's say L is the and it is clearly order L. Okay, so now what is the entropy of such a wall? Huh? I mean, roughly, what do you think? Sorry? Why? I mean, entropy means what? Like I can put it at various places, right? But I can move it up and down and do various things. It's like a polymer, right? I mean, it's like counting polymer configurations. So if you have like counted polymer configurations, is exactly that problem. I mean, it's like a self-avoiding walk, and you're just counting the number of configurations it can have. No, okay. So I mean, if you just think simply, it's like a random walk. Okay, so then each step it can take two ways, right? It can go this way or this way, and then next step it can take two ways. So if you did that way, it would be wrong, of course, because it might give you overlapping things and so on. But that would give you 2 to the power L. Okay, so which is already exponential L. Okay, so if you do a more careful calculation, like people do in self-avoiding walks, then you'll find that the number of configurations is typically like, let's say, so the simple calculation you could put it anywhere and you could have a lot of different configurations. So that would give you L times something like 2 to the power L, okay, which is already good enough. Okay. But if you do a more careful calculation, you'll get L to the power mu exponential of some power L. But the main point is that it's exponential in L. Okay. So when you take log, you get something which is proportional to L. Okay, and what is the energy cost of like producing this? It says proportional to the length of this, right? So you have now in this calculation you have okay, so we just repeat this statement. So delta U will be like, let's say, I mean, let's forget J times basically the length, and delta S is like KB it's linear in L. Okay, so now both of them are linear in L. So if you ask what is the change in free energy, so that is JL minus, okay, so compared to L, you can forget log L. So you just have minus KB T. Okay, so now you can see that if you are below some temperature, if you are if you are below some temperature, then this is what? Okay, so here what did I say? If you are at any temperature, this is large, so free energy always. Why does it go down? Okay, no, what was the argument? Go down, oh right, yeah, so that was the argument, yeah. So it goes down means you can excite them, right? So here it, okay, so this is J minus some constant KBT times L. So now if T is less than something, let's say J by CKB, then of course this is positive. So then it costs energy, right? Costs a lot of energy to create this excitation. So then you will never have this kind of excitations and it will stay in the ordered state. Okay. So this predicts that, I mean, this kind of argument already says that there should be a TC. And again, you can make this completely rigorous. Okay. So, and if you just do a simple, like, if you put that 2 to the power L, the number you get for TC is so if you do this calculation with that 2 to the power L, you will get TC equals to KB, and the actual TC is for Ising model is basically this is actual exact from Onsager's calculation. This is the TC you get. From mean field theory, you get what? Just J by, or is it 2J by KBT, right? Yeah, I think it's 2J. So 2J by KB. So that's also not bad, right? In 2D, it's already, no, sorry, it's not. Okay, so what do you get from mean field theory? 4J, right? Because 4 neighbors. So J, Ij sum over J, that gives you 4J. So from TC from 2D mean field theory is 4J by KB. Okay, so I think that is also a generally true statement. I mean, mean field theory gives an overestimate of the TC value. Okay, so the actual value is here. And you can see this Payal's argument gives a value which is not bad. Okay, and this kind of. Oh no, so this one actually I did I did this 2 to the power L. So this one I don't know actually. I mean, if you do this, I don't know this factor here. Okay, yeah, maybe I think Payal's argument gives you the exact TC if you do it carefully. Okay, so are there any other questions? Okay, if there are no other questions, then I'll give questions which you can solve during the tutorial. Okay. Yeah. No, we used in the sense that we said that the actual free energy. You're talking about this, right? Right. No, so we use it in the sense that we know whatever we are getting is kind of a close, is a close, I mean, is the best approximation to the real free energy. In that sense, we are using it, right? Because we try to get as close to this as possible. That in that sense, we are using this inequality. Because otherwise, if we didn't know this, then of course we wouldn't know what we are doing. Also, we wouldn't know what we are doing by the entire process, right? Here we know at least we are approaching whatever, by this process we are approaching the actual free energy as close as possible. Okay, so let me give some problems which you can do in the tutorial. And so what I would suggest is that in the this tutorial, you just sit here and do these problems, and maybe you can spend like 45 minutes just trying to each of you individually try, and then you can just try to figure it out amongst yourself. Like I asked a few people, so Deepak and who else was it? Prasad and someone else. Okay, so so there are a few people who will kind of coordinate it. So Deepak, can you just take in here? So so at the end of the day, you should all solve these problems. You also have tomorrow. Okay, if I have lost the problems, then it's we have lost. Okay, so first problem is proof. Okay, so this average is with respect to some probability distribution, right? That's how that's the definition. And I'm saying that this function f of x is convex in this sense that double prime is greater than 0 in some region. So I'll just give you a hint of how to do it. So basically, if you look at, so this basically means that f prime, so f prime is a function, right? First derivative of f is a function, and that slope is continuously increasing, right? So if you think of f prime as a function, then f double prime 0 greater than 0 means f prime is continuously increasing function. Okay, so now if this is true, then basically what you can write is that f prime x minus, so supposing you're kind of expanding this function about around the average value. Okay, so then there's something called the mean value theorem, okay, which you learn actually in school and then everyone forgets, but this is useful. So x minus x average is equal to, remember what? So this is like if I have some function, so I'm, so it's almost like Taylor expansion except that I'll write an x, right? Yeah, so this is like f at some point between x and x bar. Right? So this is just a. Then what you should do is, okay, and then this, what I know is that this is positive. Okay? And then this thing I should just integrate from x bar. Okay, okay, to get f of x equal to something. So basically you have f prime x is equal to f prime at x bar plus this is the same thing. And to prove it, basically what I have to, it's good to do is basically try to expand this function around x bar. Okay, so now using this, okay, if you just integrate it once, you will basically get kind of a Taylor expansion, okay, except that it it ends at some point. Okay, and if I could do a Taylor expansion, of course, I mean, like if I neglected all other terms, I would immediately get this. Like if I, but so you have to do something like that. So I won't give more hints, but try this. Then two is using this and like similar to what we did in the quantum case, proof So this I didn't go through the steps. So this you just have to fill up the steps that led to this form. Okay, so this I already like in the lecture I wrote this form, but I didn't fill up the steps. So you should work this out completely, and also do the expansion. So which includes this coefficients a of t and so on. So complete all the steps that I didn't do. So C of R. Okay, so this is of course a lot of questions, and so I mean, but by tomorrow at least you should be able to finish it. Okay, finally, one sort of independent question is supposing you take a harmonic crystal. by something like this. So this is on some arbitrary lattice. You have a harmonic crystal which has, let's say, some interactions which look like so this is so E hat here basically means sum over nearest neighbors. So these are like parts strings connected to nearest neighbors. So in general, this I can again write it in some form like J of so for this Hamiltonian compute the like okay, so this is a crystal and then there like the positions fluctuate, right? So what are the correlations in these fluctuations? So basically compute this function, let's say Q of this is like this correlation function. Okay, so this calculation should be almost identical to this calculation of the correlation function. Okay, so that's why I want you to do it. And also it's another calculation of a correlation function in a simple system where actually you also see power law correlations. Okay, so this you can do. I mean, one interesting result thing you'll get from here is if you look at Qx square. So like if you look at a given point and see how much it fluctuates, so I mean what will this be? So you have just a harmonic crystal in equilibrium. Okay, so this thing, huh? Okay, so it's, huh? Okay, so yeah, most of you think it's KBT, it's not KBT. Because, okay, so what you will find is that this is something which is, which grows as n in, so n is the, let's say the size of the system. So it grows as n in 1 dimension, grows as log n in 2 dimensions and is finite in 3 dimensions. Okay, so this is why in effect you can't have a crystal in 1 and 2 dimensions and you can get a crystal in 3 dimensions. Okay, so, and that's, if you do this calculation that will tell you. Okay, so I mean you can't use, see what is the equipartition theorems, it's only if you have isolated oscillators then it's true, right? These are coupled oscillators, so then there's no statement like Qx square is equal to KBT. Okay, so this calculation basically involves doing, so finally this object is what? Qx prime at 2 different points, and then you have exponential of minus beta, and here position and momentum decoupled, right? So you can forget the momentum, you can just take this. So you have some j x bar x prime, q x bar x prime. So this is what you have to calculate, dq at all sites. Okay, and this is just a Gaussian integral, and the simplest way to do this is maybe you can put a, like we put a magnetic field, you can put a, some force field at every site, and then there's a general formula for a Gaussian integral, right? Okay, so let me also write the integral just to, so this is the only thing you will need for this calculation. Okay, and this is a very useful formula. Okay, so actually, some of the main things that is useful for doing most of physics is like Gaussian integrals and inverting matrices and taking Fourier transforms. Okay, so this is one formula that you should really remember very well, which is like if you have a integration like a Gaussian integral in one variable. So yeah, this you keep using all the time. So it's good to remember this formula. So supposing you have just a single variable, and if you do this integral, you get okay. Huh? Sorry. Yeah. X ax. X square. Mine is ax square, but I'm just writing it like this. Okay, but, so I'm just writing it like this, and this is also f square by a. Okay, but I'm just writing like this. This is 1D integral, okay, which is very easy to do, right? Everyone has done. And so now if you have like, instead of one variable, if you have many variables, then it's basically like you have some matrix, right? I mean, so you have some like Q, this is basically some like Aij, Xi, Xj kind of stuff, right? So this is then, it's like you have a multiple integral and you have a matrix which you can write like X transpose A, X transpose X. So when, what this means is like X, you should think of a vector like that. A is a matrix and X is a vector. So, and so this is equivalent to just writing Xi, Aij, Xj, which is basically this object, right? And you're doing over all X and J. And this is also just Fi Xi, okay, but I'm writing it in this form. And this is equal to, it's just, you can look at this formula and write the n dimensional formula. So this is 2 pi n by 2 or d by 2 by, so this A gets replaced by determinant of A to the power half. Okay, and this one basically, this is some vector. So this is just F and then A inverse F. Right, so you can use this formula to compute the partition function in the presence of a field. Then you basically take log of that and do a derivative. If you do two derivatives, you will get the correlation function, and that will just be A inverse, right? So A inverse means this inverse of this matrix, and that you can find by Fourier transforms. Okay, so this I want you to just do it carefully, and then finally show that, find this object at large distances, how does it decay, and also show that it diverges in, if you look at equal point correlations, it grows in 1 and 2D and is finite in higher dimensions. Okay, I mean the final calculation is again exactly same as this, proving this Polier's theorem and so on. So it's just doing the same thing over and over again so that you kind of remember. Okay, so so I hope you will do the. X naught. What is X naught? Xc. This one. Oh no. General H naught. General H naught. Right. It's just like in the quantum case we proved for general. Right. So it's almost the same, but if you do it again, you'll just remember better. Oh, okay. No. So this is the original thing. Now you have to just write whatever it is. I mean, like corresponding to this, you can easily write this, right? I mean, like if it's a 1D thing, it will be a, J will be a matrix like maybe 2k minus k, 2k minus k minus k, something like that. Okay, so probably there are no questions.